Eh. Okay, today we are going to wrap up 2.1, which was functions. We had done that difference quotient, remember? Remember that? It was kind of crazy a little bit. There was one example that was in the homework that was a little bit different than what I did in class, so I wanted to go over something like that. And then we'll wrap up that section. We'll start 2.3. I don't think we're going to finish. And then next class we'll finish up 2.3. We'll start 2.4. And just a reminder that our exam, we're still a little ways off on the exam, but this exam 2 will cover just chapter 2. So I think it's 2.1. We skipped 2.2. So it's 2.1, 2.3, 2.4, 2.5, and 2.6. All right? Uh-oh. All right, so check out this difference quotient problem. I was thinking that someone might have a question on it, but I figure I'd just do it anyway. Specifically number 79 out of the homework. And it gives this function f of x equals x and then 20 minus x. That's it right there. And the instructions here are to find and simplify a couple of different things, but I want to talk just about the difference quotient, which would have been part C. All right, so finding this for that function. Did anyone try this? No? Okay. Let's just try and see what happens. Remember with the difference quotient, I told you to look at it like 3 different sections. There's the top left corner, the top right corner, and then the bottom, right? Those are like the 3 different areas you have to look at. And the only one that really requires work is this piece right here. This is already given to us, and this is always going to be h. All right, so let's try and figure out what f of x plus h is first. So I'm just going to figure that out and then put it all together. So what is f of x plus h? What am I going to do here? Plug what in? What do you mean? Okay, so I'm going to plug x plus h into this function, right? Replacing x with x plus h. Do y'all remember the thing I said students make the mistake of doing? Yeah, they just put an h plus h out here. Don't do that, right? You're going to put x plus h here and x plus h here. So let's go ahead and replace x plus h, 20 minus x plus h. Okay, now I did that incorrectly on purpose. I wanted to see if y'all could catch what I did wrong. I need parentheses, right? So where do I need the parentheses? This first factor right here, x plus h, I need that in parentheses. Is that it? Am I good? And the other one. Now, the other one is the one that's really tricky because you're subtracting x, right? But if you replace this with x plus h, that means you're going to subtract the x and the h. And if you don't put the parentheses there, you're going to miss it because you're not going to get that minus h in there. We good? All right. That is f of x plus h. That's supposed to go in this top left corner. Now, before I actually put it in there, I'm going to try and clean this up. I'm going to try and get rid of some of those parentheses and combine everything together, multiply it out, just so it looks a little nicer. And the reason is because, do you all remember what I said should happen if you do this correctly? I said it kind of at the end of class, so I'm not sure if you'll remember it. Things will start canceling out, and everything that you have left should have an h in it. All right? If I have everything trapped in parentheses, then I'm never going to get things to cancel. So right now, let's start by distributing the negative through. So x plus h, and then 20 minus x minus h. And now what I'd like to do is try and multiply this together. So that was just the negative sign being passed through, right? Okay, now a lot of you are really good at multiplying, you know, a binomial 2 terms times 2 terms, but how do we do 2 terms times 3 terms? You distribute, right? You start with this x, goes here, here, and here. So you're going to multiply those 3 things. And then after you do that, you're going to pass the h through, same way. H here, H here, H here. So we're going to have a total of 6 multiplications, which should give us 6 separate terms. So what's our first term? 20x, good. And then next one, minus x squared, good. Next one, x times negative h, so minus xh. So we've done the x through. Now we do the h through. So next term, plus 20h. Next one, minus xh again. And then minus h squared. Good. We all good with that? Okay, can we combine any of these together? Do we have any like terms here? Yes. Yes? Which ones? Negative xh and negative xh. That's really like negative one of those, and if you put those together, you should have negative 2 of them. And that's it. Those are the only like terms I have. So I'm going to do that. That'll be my last kind of step. I'll put it right here in minus 2xh. And then I still have the 20h and minus h squared. So this right here is not our final answer, right? I'm boxing it, but that's not our final answer. That is just f of x plus h. That's it. Now we have the pleasure of going back into the formula for difference quotient and plugging it all in. So here we go. The difference quotient is going to be f of x plus h, which is everything I just found. I'm going to write that down. 20x minus x squared minus 2xh plus 20h minus h squared, right? And then minus f of x. And f of x is given to us, right? It's this right here. So all I need to do is put that on the top right corner here. And let me write it down. You tell me if this is okay, or if I need more parentheses, or if that's okay like that. What do you think? Is that okay for me to just put the f of x right there like that? No. Okay, so, oh, you're going to want me to distribute this? I will do that, but just the way it's written, is that okay? It is okay. Now, I told you to be careful with this because that minus sign has to distribute through everything. But because this is 2 factors, 2 things multiplied, it's okay to not, you don't need an additional parentheses around this, right? Because you can look at this as a negative x, that negative x will pass through, right? So I'll distribute on the next step. Let's go ahead and divide this whole thing by h, right? So that is the difference quotient. It's just not cleaned up yet, all right? We're going to clean it up. So let's go ahead and pass that negative x through. I'm going to rewrite this entire line, so that line's equal to 20x minus x squared minus 2xh plus 20h minus h squared. And then what? Minus 20x, and then plus x squared, right? Negative and negative is positive. All of this over h. Now, good things should start happening, all right? We should start to get that cancellation. So what goes away here? The x squareds cancel out. Anything else? 20x goes away. And do you see that everything that's left has an h? All right, that's a good thing. I'm going to rewrite here negative 2xh plus 20h minus h squared. That's it, right? That's the only, I feel like I'm missing something. No, there's those 3. And then over h. And now, because everything has an h, you can factor out an h out of the numerator. So let's factor an h out. Our ultimate goal is to get that h to go away, to cancel. So if I pull an h out of the top, I can cancel it out. And this is where we stop, okay, after we pull this h and cancel. So that's equal to h comes out. What will I have if I factor an h out of this? Minus 2x plus just 20 minus just h, right? Because you pulled one of the factors out. All over h. Now they can cancel out. And what's in parentheses is our final result. Now, if you recall from last class, what I told you was that our goal in here is to just be able to do this algebraic manipulation. And then in the next class, Math 1325, we actually do something more to this, right? But for here, we just want the mechanics. We want to be able to do the mechanics part. That reminds me, faculty are choosing our schedules for the spring semester. And I think I told you I haven't taught 1324 like face-to-face, right? I told you that. So I'm considering doing, like, trying to pick the 1325 for spring. But I only want to do it if I have like a good group of people that would want to take it. So I think next class I'll pass around an anonymous survey. If you would like for me to teach that class, then I'll at least request it, okay? Or if you want me to just go back to teaching other things, then I can do that too, all right? You won't hurt my feelings. All right, any questions? Y'all understand this? This one was a little different than what we did in class, for sure, right? Now, I will also point out that the original function, all right? The original function was f of x equals x times 20 minus x. You could have started this problem by just distributing the x and used that as your f of x and done everything the way we just did it, and you would get the same exact answer. All right? So if you want, you can try it that way. The algebra is a little different, but you should still get to the same place. Understand what I'm saying? Okay. All right, that's it for that. Now we're gonna finish up 2.1 by actually talking about some things we've talked about before, but putting up like more precise definitions, because we're going to need them to do the word problems in the next section. So let's review the cost function. We're going to talk about business functions, things we use in 1324 and 1325. So our cost function generally looks like this. Cost is equal to our fixed cost plus what we called our variable cost. Do y'all remember me talking about this? That'd be like, you're running your business. You're going to have the fixed costs, which are maybe the cost of electricity or things that are not going to change. Whether or not you produce a single iPhone or not, these things are always going to be there, right? And then the variable cost are things like, okay, well, if we have 20 people working on a project, that could change depending on how many items we want to produce. So these things change, these things don't, right? So one way we could represent this is, and I want to use the same variables that the book does, we could say that the cost is equal to A plus BX. So A is our fixed cost, and then B times X is our variable cost. And here X is going to be the number of items manufactured. So A and B here are usually just numbers, all right? And this is a linear equation. It looks like y equals mx plus b. Actually, y equals mx plus b. So the letters are a little different, but it's linear, right? This is a linear cost function. Now, we also have the price demand function. Now, think some of you struggled with the price demand function on the test. That was where I gave you a few things about, a few pieces of information about, I think, what was it? What did we do on the test? Was it phones? It was phones, right? It was, at a certain price, the demand for the phone was, I gave you 2 data points and you were supposed to create a line, and that would give you your price demand function. So this usually looks like P equals price equals M minus NX. And here X is the number of items which can be sold at price P dollars. What type of equation is the price demand function here? It's linear again, right? It looks a lot like y equals mx plus, mx plus b. All right, so we have a linear cost function, a linear price function. Now, revenue function is this is new, okay? We've talked about revenue. We've talked about the revenue function, but now we want to formalize it a little bit more. The revenue function. Do y'all remember what the revenue is? What's revenue? Not profit. Okay, so we need to make the distinction between profit and revenue. Which one?
You said revenue?
Revenue, yes. It's revenue. Okay, so remember, you have money going out as a business, right? That's your costs. You have money coming in. That's your revenue. The difference between the two is your profit. All right? So this revenue function is just the money coming in. And we can actually write it this way. Wouldn't it be the number of items sold times the price per item? So if I sell 1,000 iPhones at $450 a piece, right, then my revenue would be the 1,000 times the 450. So it's the number of items I'm going to sell, or I'm able to sell, times the price per the item. All right, can you tell me in terms of our variables that we have on the board so far, what is the number of items that we could potentially sell? X, right? X is the number of items we make. X is the number of items which we can sell, right? And if we sell them, the number of them we sell would be X. So we put X here times what's the price per item? P, right? That's our price per item, times P, which if you replace P with that equation, you get this new revenue function. That the revenue is X times P. So this is something you need to remember. This is going to come up throughout the rest of the semester and even into the next class. Your revenue is X times your price. In this particular model, our price is given by this, so that's what we plug in there. Understand? All right, next thing, let's talk about profit. Now we can talk about the profit function. Our profit function is profit equals revenue minus cost, right? Money coming in, take away the cost of running our business, that's our profit. So in terms of what we have on the board, and please don't confuse the capital P with the lowercase p. I know these may look confusing, like the same P, but these aren't the same. And in the book, it's easier to see that it's lowercase versus capital, all right? So the profit should be my revenue. What's my revenue? That thing over there, right? This? X m minus nx minus my cost. What was my cost? I erased it. A plus bx. Now, is this correct for me to write it like this? I need parentheses, right? So do you all see that this is profit is revenue minus your cost? Okay, now we need to step back and take a look at that for a second. Let me clear the parentheses. That means let me distribute the x through, let me distribute the negative through, and we'll just kind of take a step back and take a look at this. Xm minus nx squared minus a minus bx. All right, so just distributing through. Does it matter if I write x times m or m times x? Like, does this order matter? This doesn't. With multiplication, it doesn't matter what the order is. So I could put xm or m times x. So this is my profit function. Any questions on how I got that? No? All right, so let me give you a specific example of a profit function. M, N, A, and B are all just numbers, and then X is our variable, right? So I'm just going to make up some random numbers here. Profit equals, let's just say, I'm going to replace M with 3, X. I'll replace N with 2. So 2x squared. I'll replace A with 5. I'll replace B with 10. Okay, there we go. That's what we have. So I'm just giving you a specific example. If I actually had given you numbers, you know, M, N, A, and B, then you'd have something like this, right? Do any of y'all recognize this type of function? Quadratic. You probably saw this in high school. This is called a quadratic function, and the reason why is because your variable is being squared, right? So our goal today, moving into 2.3, is to be able to get a handle on what these look like, how to graph them, and then try and connect them to this profit function, like put it into a business model.
Like word problems.
Like word problems, sorry. I was trying to not say that, but as soon as I say that, people usually don't like it. So, all right. All right, so I think this is a good place to end this section, is to just say, okay, we've got this type of function. What do they look like? Because let's say I had some visual representation of this function. It would represent my profit, right? Do y'all know what these look like? I mean, we're going to talk about it, but
It's like a U, right?
it looks like a U. Okay, so let's say, maybe I can talk about this before we actually get into it formally. These are called parabolas, but they look, I'll just say this one. Let's say this one looks like this. Okay. Let's say this is our profit function, this parabola-looking thing. What do you think I would be most interested in on this graph? The highest point, right? Wouldn't that be a very interesting point for me to figure out? To say, hey, what was the X that gave me this point? Because if I can find that, then I have figured out when my profit is the highest it can be. And so this is what I want to shoot for, right? X, remember, is the number of things we sell. So if I sell more than that, you may think you're going to make more money, but it turns out with this model, selling more would actually reduce your profit. And if you sell less, it's going to reduce your profit. So there is some optimum solution that we're going to look for. All right? That's the whole idea here. All right, so let's talk formally about quadratic functions. We need to get some of this stuff out of the way, and then we can start doing the word problems. All right, quadratic functions, 2.3. Now, quadratic functions are usually looked at in two different forms. In other words, when we write a quadratic function out, there's two kind of standard ways they look. All right, so I'm going to give them both. I'm going to give them both to you at the same time. All right, so the first one, f of x. Okay, so that's our notation from last class. We are looking at a function, and remember that means when I graph it, it will pass that vertical line test, right? When we look at it, all quadratic functions can be written like this: ax squared plus bx plus c. Now, a, b, and c are just numbers. X is the variable. So I'm going to write down a, comma, b, comma, c are numbers. But we do have one restriction, something about a. Can somebody tell me what a cannot be? 0. Okay, because if a is 0, then this is actually gone, right? If a was 0, this isn't even here. And then it's no longer quadratic, because now you have bx plus c, which is going to be linear. So we need to have this restriction that a can't be 0. All quadratic functions can be written in this form. Now this is called the standard form. And I'll do an example here in a little while, and I'll give you a specific quadratic function to look at. Now the other form is going to look weird, but here's what it is. F of x equals a times x minus h in parentheses, that quantity squared plus the letter k. Okay. Here, a, h, and k are numbers. And again, a cannot be 0. Because if a is 0, this whole thing is dead, and all we have is k. So it's doesn't even have variable in it anymore. This is called the vertex form. Now, with the vertex form, right now it's hard for me to explain what's nice about this form. But as we talk now about what these things look like, I can connect it back to this. All right? But these are our two standard forms, or the two forms of quadratic functions. All right, so let's look at their properties and their graphs. Show of hands, how many of you have seen quadratic functions already? Almost everyone? Okay. All right, so this isn't brand new material. All right, properties. I'll just say properties. Properties of quadratic functions. We basically have, when we look at the graphs of these, I forgot to put parabolas up here. Parabola. So quadratic functions are also called parabolas. When we graph these, all right, we have really one of two cases is going to happen. The first case is if the a we have is bigger than 0. So I'll put if a is bigger than 0. Does anyone know what the graph's going to look like? I mean, we know it's a U, right? Which way? Up. Okay, so this is what the graph winds up looking like. Here's my x-axis, the y-axis, which I'm going to call f of x. Our parabola would then have to open what we call up. It would look like a smiley face. So maybe like this. I'll draw another one here. It may have this. And just about any way you can think of drawing a U that opens up, all right, that would be a parabola. That's what it would look like if a was bigger than 0. Now, what about if a is less than 0? It's going to point down. So same thing. It's going to go down like this. Maybe like this. I'm just giving you like 3 examples of each one. Okay, so here we say it opens up. Here we say it opens down. So that's pretty easy. Well, historically, students usually have no problem with determining if a parabola opens up or down. Because all you have to do is look at this number and figure out if it's positive or negative, right? If that number is positive, it opens up, negative down, positive up, negative down. That's it. But there are other aspects to the graph that we need to be familiar with. So what I'd like to do is I'd like to just take one of those pictures. I'm going to pick one of those and let's just focus on just one and start labeling some things on this graph. And I'm going to do this one right here. Okay, this parabola opens up, right? So A is positive for sure. The point that we might be interested in here would be this point, which is the lowest point on the graph, right? This is the minimum on this graph, not the max, the min. This is called the vertex. And it's a point, right? It's a point on the graph, which means it should have an x-coordinate and a y-coordinate. Well, the vertex is such a special point that we actually use not x and y, but h and k. Now, you remember a second ago we put the vertex form of the quadratic function up there and it had h and k in it? This is how it's connected to the picture. If you're given a quadratic function in vertex form, you can actually identify this point right away. And we'll do an example so you can see what I mean. That's called your vertex. And then we have this imaginary line. This is not part of your graph. But this line right here is called the axis of symmetry. And symmetry, coming from the word symmetric, meaning that we have, this is like a mirror image of itself. If we take the left side of this parabola and we just mirror it over that dotted line, it will land right on top of the other side. So we've got this axis of symmetry. Now, it's a vertical line. It's a dotted vertical line. And the equation of a vertical line is x equals a number. Can anybody tell me what number it would have to be in this picture? H. Very good. X is equal to h. That is the equation of the axis of symmetry. Because the h is the x coordinate, so our line x equals h defines this dotted line. Just remember, it's not part of your graph. It's just a visual aid to help you when you're graphing these. When you look at it, it should look symmetric over that axis of symmetry. All right, what else might be interesting for us to know about this? How about the domain? Can you tell by this picture what the domain would be? Infinity? Okay, so you mean everything, right? It looks like this graph goes in both directions forever, right? Just keeps going and going and going. It widens out as we go. So we should be able to plug in any value of x and get an output. So the domain, the way we set it, we used interval notation, negative infinity to infinity. What about the range of this one? That's what comes out of it, right? These are the y values. So can you tell me about the y values? Do I get outputs over here? No? When do I start getting outputs? Right there, when I get to the vertex, right? And then the rest of the way up to infinity, right? So where's this starting point? K, very good. It's the y coordinate of the vertex. That's where it starts, and then up to infinity. So we've got from k to infinity, and I'm going to put a bracket or a parenthesis on k. Bracket, because we actually do get that value. K actually does come out of the function, so k to infinity. All right. What else? If it opens down? Yes, I'm going to do down on a different picture, just so we can separate the two. All right, what about, is there anything else on this graph that, if this were a business model, that might be interesting, like that might be of interest to us? Okay, you're talking about like a break even? Are you talking about where they hit each other?
Right there in the line.
Oh, these right here? Oh, yeah, okay. The x-intercepts.
Yeah, there you go.
There you go. Yes, those are definitely important to us. Right here. Now, again, if this were profit, then what would those 2 points be telling you? Where you're getting zero profit, which means where you're breaking even, right? That is zero profit. Profit being zero, remember, profit is revenue minus cost. So you'd be saying revenue minus cost is zero. But if you move the cost, add C to both sides, you're saying revenue equals cost. So for us to find where this is zero is equivalent to us asking, where do we break even? All right? And that's what we want to do here in a little while. We're going to ask two questions. Where's our break even? And where do we get maximum profit? That's what we're going to shoot for. Again, I don't know if we'll get to it today. What time did we start? Oh, we still have time. Okay. All right. So yeah, these x-intercepts, very important to us. X-intercept. This is an x-intercept. Anything else that might be of interest? Y-intercept. Okay, this right here. Y-intercept. What would that represent? If this were a profit function, what would the y-intercept represent?
You're starting out at.
Okay, good. What you're starting at. Basically, if you don't sell anything, right? Because X is how much you're going to sell. If you don't sell anything, this would give you your profit for that. Now, this is not a good picture because this is saying that if you don't sell anything, you're going to make money. And I'd love to be part of that company, right? That you just don't even have to do anything and you just make money. That'd be great. But that's what the y-intercept would represent. Okay, that's what it would be if this were a profit function. All right, well, most likely your profit function is not going to look like that, right? It's probably going to be flipped the other way around. So let's take a look at another quadratic function that's flipped over. Let's identify the same points. The things that's really going to change here is this. This range is going to be a little different. So let's just graph it real quick. And then we have to talk about the x-intercepts because there's something kind of subtle here we need to make sure we understand. All right, so what if we have a picture like this? And this one, I'm going to make this one look a little bit more like real life. If this is x, this is f of x. And I draw a function that looks like this. All right, now the parabola is going to continue here like that. Okay, so we know here for this quadratic function, a would be negative. We do have a vertex. We still have that, right? HK. We do have, in this case, two x-intercepts. We do have an axis of symmetry. We do have a y-intercept. Now, do y'all see how this makes more sense? If we don't sell anything, right? X is how much we sell. If we didn't sell anything, then we would be what? Negative profit. Negative profit means you're losing money, right? All right, what about domain? In the picture, what's the domain? Has it changed from this? No, the graph goes, right? For every x you plug in, you get something out. Now, when we start doing word problems, our domain is going to be restricted because in a word problem, we can't have negative x because that would mean we're selling negative amount of things or we're manufacturing a negative amount and it won't make sense. But in general, with quadratic functions, the domain is all real numbers. You know, mathematicians tend to be somewhat dull people. I'm making a very big generalization there. But we are still pretty funny guys and girls. Do you know what we call infinity in mathematics? You're going to think this is hilarious, I know. We call it lazy 8. Isn't that funny? Is that horrible humor? I don't know who told me that, but lazy 8, sleeping, right? Taking a nap. It's terrible.
Not the actual joke.
All right, what about the range? What about our y values? How is it different in this one?
Negative infinity.
Yeah, see, it goes down forever here, right? Negative infinity. But it stops where?
K.
At k. So we need to write that negative infinity to k. All right, since y'all didn't like that joke, I'll give you something better than that. All right. All right. This is what we consider a surface, right? How many sides does it have? Two? Okay, so my index finger is on one side, thumb is on the other side, right? Y'all agree?
Yes.
We can agree that that's two sides? Okay. If I take this strip of paper and I twist it one time and I paste these together, and I just happen to have a stapler here, I've created this. Now, does this still have two sides?
Yes.
You sure? It's one-sided. So here, let me show you. If I get my index finger and my thumb and I put them together, then if I just start at my index finger and start going around, I will actually be on the same side my thumb is on, and I'll come back around and I'll be still on the same side that my index finger is on. So my index finger and my thumb are actually on the same side of this. So this is an example of what we call a one-sided surface. It only has one side. Kind of looks like infinity though, right? A little bit? Does that kind of look like infinity a little bit to you? I've always thought of this as being a good idea of infinity, because if you were a little ant, right, and you just started walking along this, you would walk forever, right? As opposed to an ant that walks on this, that would hit a boundary, right? So this is like an infinite path. Just keep going around, as opposed to, all right. That's better than lazy 8? Okay. More interesting, that's what I mean. Okay. All right, let's get down to business. X-intercepts, we have two. Let's talk more about X-intercepts. That's weird, right? A surface that only has one side. There's also there is such a thing as a container that has no volume to it. It's called a Klein bottle, but it's beyond anything you would see in this class. We call it Klein bottle, but it's a container like a cup, but it has a zero volume. The inside of the container is the outside. It's complicated. I'm not going to try and explain it. But the story that I have is when I graduated from college, one of my buddies got me a Klein bottle mug, beer mug. And my buddy owned a bar, so I would take the beer mug to my buddy's bar and he would fill it up and I wouldn't have to pay for it, because I explained to him it's a volumeless container. So the beer was in there, but I was really not drinking any beer because it had no volume. So anyway. All right, X-intercepts. Question, how many can we have? In general, okay? In general, how many can we have? If we have a parabola, 2, we can have 2. I've already drawn that picture. Here's an example. We could have 2. Is there any other possibility? What? Well, let's keep it either down or up. Because if we start turning it this way, it's a different type of parabola. We're not going to. You could have what? None? Okay, how could I have none? If I draw this and I want to draw it, let me draw this one up. I'm going to draw this parabola up. So you want it to be where? Above the x-axis. So you could actually have none. Any other possibilities? Just one. How do you get just one? The vertex is hitting the x-axis. All right. How about like that? I'll make this one go down. Are there any other possibilities? There are no other possibilities. With all quadratic functions, when it comes to how many x-intercepts we can have, it's either 0, 1, or 2. That's it. 0, 1, or 2. No more possibilities than that. Now, most of the functions we will deal with here will have 2, but this is just for us to be aware. Now, we're going to start getting into where I'm going to give you a function and we're going to try and graph it and get all of its characteristics out. But there are 2 more things we need to discuss before we do that. The first one is, how do we find x-intercepts? How do we find them? Like, if someone gives you a quadratic function, how do you find the x-intercepts? How do we find the x-intercepts of a quadratic function? Well, how did we find the x-intercepts of a line? Remember when we had this thing, ax plus by equals c. This was a line. If we wanted to find the x-intercepts, we set y to 0, didn't we? Okay, we set y to 0. Well, when we have a quadratic function like this, remember the f of x is really the y, isn't it? That's the y coordinate. So if we follow the same method to find the x-intercepts, we want to replace this with 0, don't we? This side. So what we get is this equation. So basically we set function equal to 0. And when we started this class, there was a packet of problems that you were supposed to do, right? And one of the things in there was solving quadratic equations. Can anyone recall the methods we used to solve quadratic equations? You can factor, maybe, right? It might work, it may not. And if that fails, quadratic formula. Okay, the quadratic formula. So at this point, you either factor, if it's even possible, or use quadratic formula. And I'm sure you all remember the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. That look familiar? Remember working with that? All right, so if we're able to, if we're ever trying to find the x-intercepts, which we will because that will be profit 0, which is break-even point, right? Then we're going to have to solve a quadratic equation and use either the formula or factoring. All right, we'll do one with an example. Any questions on that, though? All right, so that's the x-intercepts. Last thing, and then we'll do an example. How do we identify the vertex? The vertex is such an important point on a parabola. How do we actually identify the vertex? Well, it turns out that there's going to be 2 different scenarios. The first scenario, case 1, if our quadratic is actually in the form like this, that's called the what form? Vertex form. Why do they call it vertex form? Because what can you actually identify by looking at it? The h and the k is just like looking at you, staring at you. There it is, h and k. So that's the vertex form. So all we do is just look at it and we get it, right? HK. And again, I'll do an example, like it's right there, right? Oh, I put those arrows in the wrong place. Or HK are there. So that's the easy case. Someone gives us a quadratic function. It's in vertex form, so we got the vertex. Case 2 is if it's in standard form. And this one, there are several ways you can do it. One of them is tedious. And in a normal like college algebra 1414 class, we definitely want students to know how to get the vertex from this by using a method called completing the square. Have you ever heard of that, completing the square? It's something that you need to be able to do by hand if you're going to do a lot more math. But in a business class, what we can do is we can actually take a nice result from Calculus 1, and in Cal 1 we actually are able to create a formula that gives you the vertex from this. So that's what we're going to do. It's called the vertex formula. So the vertex formula, I'm out of room, let me move up here. So we can think Isaac Newton and Leibniz, the two fathers of calculus, we can thank them for the following formula. So we have this. The vertex in this form, h, right? H is just this number, whatever. That h will always be negative b divided by 2a. That means you're going to take this number, whatever it is, take the opposite of it, negative b, and then you're going to divide it by 2 times that number. So it's just like a little plug and chug, and that's it. Just plug it in, get a number, you're done. That'll give you h. Now to get k, all we have to do is take that answer that we just got right here and plug it into the function. So I'm going to write f of h, and then we'll be done. So again, I've given you just a bunch of formulas and ideas and theories, but now let's do an example. Our goal is going to be to sketch a quadratic function. We're going to identify the vertex, axis of symmetry, x-intercepts, y-intercepts, domain, range, everything, all right? But we're going to have to do a lot of work to do it, all right? We good? You'll know what we're about to do? All right, here we go. So our first example, and I'm going to give you a very, very basic quadratic function to start with. When we start doing word problems, we're going to have decimals and all sorts of things like that. We'll need our calculator to do a lot of the computations. This one, I'm making it so that we can do most of it just by hand, all right? So our quadratic function is x squared. Which one do I want to use? Let's go minus 4x plus 3. All right, so this is a introductory problem here. What I'd like for us to do is I'd like for us to sketch this. And what I mean by that is I want the vertex, I want the axis of symmetry, I want the x-intercepts, the y-intercept, anything else, domain, range, the max or the min, all right? All right, here we go. What would you like to start with? Well, let me tell you what I start with, okay, and what I recommend you do first. First thing, determine if this opens up or down. Okay, so I'm going to give you some steps here. First step, up or down? Okay, it's what? It's up. It's up because why?
A is not negative.
A is actually 1, isn't it? Which is bigger than 0. So the number in front of x squared is 1, so this thing opens up. So I know that, right? Step 2, find the vertex. How will we find the vertex? The vertex formula, right? The vertex. You know what? When I wrote case 2, I never wrote vertex formula, did I? I just gave you the formula. So please go back. When I put case 2, write vertex formula, and then that h equals negative b over 2a. And then k is f of h. That's called the vertex formula. This is the vertex formula. That's how you get k. We're good? Okay. All right, so I'm going to use the formula. So h will be for us what? Be careful here. Negative b, right? What is b for us? B is the number in front of x, so it's already -4, isn't it? So I'm going to have to make it a -4. I'll actually write it out. -4, then over 2 times a, what was a? 1. So you get 4 on top, 2 on the bottom. This is just 2. See, this first example, the numbers are nice, all right? So h is 2. Okay. Now we get k. So how do you get k? Take this answer, plug it into the function. So you're going to take 2 and actually plug it in for x. We did that last class, evaluating. So what happens when we plug 2 in there? We get 2 squared, right? So that's 4. 4 or what? Minus 4 times 2, so minus 8, right? And then plus 3. And what is that? What's that?
-1.
-1. Okay. So we've got 2 numbers, h and k there, right? So I'm actually going to write down hk. The point is actually the point, what is it? 2, -1. Okay, what's next? We got the vertex. I don't care. What do you want to do next? We know it opens up or down. We got the vertex. What's that? You want to get the x-intercepts? Let's go with the x-intercepts. That's fine. How do I get the x-intercepts? Set the function equal to 0. How would you solve that? You can factor or the quadratic formula. Those are your 2 options, right? Were you thinking take the 3? Yeah. Okay, be careful with that. You can only, that's a danger zone, because if you move the 3 over, and then I think you might have pulled a GCF out there, you can only do that if that's a 0 on this side. So how about factoring? I'm going to leave this, I'm not going to show this work here, okay? Because this is our first example, and I'm going to assume that you can factor. That might take you a little time to get from here to here. But are you all comfortable with the idea of what I did to do that? Once you factor it, you set the 2 factors equal to 0. And you get x is 3 and x is 1. All right? So these are actually 2 points on our graph. 3, 0, and 1, 0. Questions? No? All right. How about 4? Let's get the y-intercept. How do you get the y-intercept? Set what to 0? X. You plug in 0 into the function. Okay? So instead of calling this 0, that's how you get x-intercepts, you replace the x with 0 to get your y-intercept. So all I'm going to do is plug 0 into the function and get 0 squared minus 4 times 0 plus 3. And so you just get 3. So this gives you a point 0, 3. 0 went in for x, 3 comes out for y. I believe that's everything I need to graph. I've got the vertex. I know if it opens up or down. I've got the x-intercept.